This is screencast 3 for week 5, 571. I was starting to talk about the issues of the issue that we have an X chart being willing to give signal if the mean shifts or if the standard deviation shifts. And so, as I say here, you can't be running an S chart in parallel because subgroup size with an X chart is 1, so you can't be computing within subgroup standard deviations. And so an obvious retort is to run an R chart. Well, it has been found through both experience and simulation and some theory that the R chart really doesn't bring anything to the party, in that your X chart will squeal and the R chart may or may not squeal. And if it doesn't squeal and it turns out there's a standard deviation shift, then you might as well not have been running the R chart. So remember, if mu shifts, the remedy is often inexpensive, because actually most of the time something has gotten out of adjustment. Fix the out of adjustment condition. But a sigma shift often means worn tooling, especially bearings. So I'm speaking strictly in a manufacturing setting right now. Bearings or waves. So on a big mill or a big lathe, numerically controlled or not, the heart of these machines are two things. First, the spindle bearings, which can be incredibly expensive because they hold very tight tolerances, but also the sliding surfaces by which, say, the tailstock moves on. Once those waves become worn, that machine either has to be very expensively reconditioned, or it's just junk. It doesn't matter the quality of the spindles. If your waves are worn and you can't keep the tailstock in the right place, and we're talking, half a 10,000th of an inch, then the machine is useless. But tooling, bearings and wear often cause higher variance than before, and that means this is very expensive to fix. And the only way you'll get your variance back under control is if you basically either pay for a complete reconditioning, or you buy brand new machines, and the latter, of course, is going to really set you back. But in a service operation, we have found over many experiences, well-trained people exhibit low variance. In performing their jobs. Their service operation. It is said just to take a sports application, it is said that you can tell the difference between a amateur star basketball player and a professional basketball player by the consistency of their ability to shoot a long ways away from the basket. A professional will have a miss rate which doesn't vary a lot over many shots, but an amateur will sometimes have a good night, sometimes have a bad night. They just have lots of variance in their performance. That is the mark of someone who's not a professional. So training, of course, is expensive and long term for most fairly complicated jobs. And you can see lack of training simply by looking at metrics on the service operation and computing their variance. The better the training, the lower the variance. So if you switch out people who are well trained and bring in new people, you can expect variance to go up. Now, variance is the Antichrist according to Six Sigma. Variance has to be abolished, reduced to zero according to Six Sigma. So if we're cruising along with our X chart and we get a signal, it's going to be really interesting to us as to whether or not the mean is shifted or the variance has gone up, the standard deviation, the square root of the variance. So how to tease apart the cause of an X chart signal. So you are in a state where you have received signal off your X chart. You've got to decide whether you should go after a something being just out of adjustment, or whether you have a more serious problem which may point to tooling or training. So you need to have the answer to the question, what caused the signal? Was it a mean shift or a sigma shift? Did the process mean change, or did the standard deviation of the process change? So Sullivan and Woodall, two well-known guys in the statistics of quality, published a paper many moons ago, 1996, on a likelihood ratio chart that they proposed to answer that question. So it would be run in conjunction with an X chart. So they proposed a likelihood ratio chart. This is complicated. You probably never thought you'd hear me say that, but this is complicated. It's explained in some detail in Ryan, but Ryan noticeably does not point to any software that you can use to implement their idea. You're in for a bit of work if you want to put their ideas into practice. I have a much simpler solution, and I have a SAS program that implements it, at least gets you started. So what you do is this. You've got your X chart. You're monitoring X, and here's stage 1. And then you start monitoring in stage 2. Now remember, in stage 1, you've established statistical control, so everything's okay in stage 1. The mean and the variance have not shifted. And you're going along, and at the n-0th point, you get a signal. You got your limits, and say you get a point up here. Upper control limit, lower control limit. Well, what to do? Here's an idea. Here's the point k plus I. K, remember, is the number of stage 1 observations. Let's let I run from 0, 1, 2, on up to n0 minus 2. And we're going to need to have n0 be greater than or equal to 2. So let's say I is 0. Then k plus I is just k. So let's divide the data into 1 through k plus I, and then k plus I plus 1 on over to n0. So partition into 2 groups. And compute the sample variance in each group. So n0's got to be bigger than 2. That means that this isn't going to work. My little plan here isn't going to work if you get a signal on the first observation, because I'm going to need to compute the variance of all the observations above k plus I. So if I only got 1 observation, I can't compute the variance. I got to have 2. That's why I have n0 equals 2. So how do you do this? Well, S1 squared, which is the sample variance, is 1 over k plus I minus 1, sum j equals 1 to k plus I of what? Xj minus x bar 1, where x bar 1 is 1 over k plus I, sum j equals 1 to k plus I xj. What about S2? Well, S2 is 1 over n0 minus I minus 1, sum j equaling k plus I plus 1, little annoying on all the subscripts, on up to n0 plus k of the quantity xj minus x bar 2, where x bar 2 is 1 over n naught minus I times the sum j running from k plus I plus 1 on up to n naught plus k. See, what I'm doing is I'm partitioning, let's say you got a bunch of points here. I'm partitioning this group and this group. And since I don't know where the problem occurred, I'm having to try all possible groups starting from the very beginning of my observation period on up to my current point k plus I. So what am I going to do with this? Well, in your 210 book, you're going to find that you are on paper trained to perform an F test for the equality of variances. It's in your 210 book. Most instructors don't bother with it. It's a very important test. And what we're going to do is we're going to form a test statistic by taking the ratio of S2 squared divided by S1 squared. And we're going to find a p-value off of the F distribution. So this is the Fisher's F distribution with n naught minus I minus 1 and k plus I minus 1 degrees of freedom. And there's a point right here, which is the computed test statistic from our two variances, the ratio thereof. And the area from that point on out into the tail, this area, is the p-value. And you know what p-values are from your 210. If the p-value is less than alpha over n naught minus 1 for a particular I, reject h naught that sigma squared 1 equals sigma squared 2 and declare a sigma shift. And you declare that to senior management, because senior management may have to go out and get a big giant loan and buy new tooling. Otherwise, they're going to stay in a state of being out of control. So you're going to be the bearer of bad news. So you better be really sure of yourself. Otherwise, you will be discredited. Typically, alpha equals 0.05. Now, the thing to be clear about this is you're not going to do this once. You're going to do it for I set to 0, then do it again for I set to 1, then do it again for I set to 2, on up to n naught. What did I say? Let's see here. N naught minus 2. Because at the other end, this group has to have greater than or equal to observations in it. Otherwise, we can't compute the standard deviation. So this looks like a lot of work. By the way, the Woodall and Sullivan paper also has you doing a sequence of tests. You're thinking this is just too technical, too annoying for me to have anything to do with it. Well, you know, maybe now, but if you get yourself a good job as a supply chain analyst, and some fast-talking consultant shows up recommending that you guys buy a whole bunch of very expensive software, guess who's going to be asked what their opinion is? You. And your technical abilities will be put to the test. And if you don't know what you're talking about, the way senior management works, been in my experience, is they never tell you you don't know what you're talking about. They just pass over you when promotions and raises are being talked about. So either you do something like what I'm about to show, or you hire outside people to do what I'm about to show you, a SAS program that I've written. And you then have to supervise their work. Often with consultants, what you have to do is take over what they have done so that when they leave, their contributions are stay with the company. So this is taking its sweet time loading up. So I think I will end this screencast and show this example on the next one.